Okay, all seems to be set. So thanks, Emmy, for the very kind introduction. So I'm very honoured and very humbled to be invited to give this Belz lecture. Of course, it's really disappointing we're not here in person, and hopefully this is the last Belz lecture that won't be in person. And for all of you not in Melbourne, envying your freedoms very much, but hopefully it won't be too long. I'd also like to commence by acknowledging the traditional owners on the lands in which we meet, which for me is the Bunurong people of the Kulin Nation, and I pay my respects to their elders, past, present and emerging. Emmy's talked a little bit about, the Belz lecture is the big event of the year, and I'd like to talk about Belz for a moment myself. So I didn't know Maurice Belz personally, but all of us in some way would have benefited greatly from his legacy and his vision to create the first Department of Statistics in Australia, which was in 1948. I decided to do a little digging around and see how that 1948 time compared to other well-known departments of statistics were established worldwide. So the first I could find was the University College of London Department of Applied Statistics, which was way back in 1911, so it predated the University of Melbourne by a few decades. But in the USA, they were a bit slower off the mark, and the first was Stanford University Department of Statistics in 1948, so the same year as Melbourne. University of California at Berkeley Department of Statistics, 1955, and then Harvard in 1957. So Maurice Belz's vision to establish the Department of Statistics at Melbourne Uni predates many of the USA powerhouses in statistics. So coming back to the first lecture, there's a note on the SSA site that promoted the lecture. It talks about the notice in 1969. The first Maurice Belz lecture in honour of Professor Maurice Belz will be given in so-and-so here on Tuesday, November the 25th at 7:45 p.m. And the first Belz lecturer in 1969 was Professor Warren Ewens, and he was quite important to me personally. So Professor Ewens, he's now an emeritus professor at Department of Biology at University of Pennsylvania in the USA. He was at Monash University in 1978 to 1996 as Professor of Math Stats, and he did his undergraduate degree in Math Stats at University of Melbourne, graduating in 1960. I emailed him a couple of weeks ago to see what he remembered about doing subjects, studying under Belz himself, and he happened to be online right at the time when I emailed him, and he responded back in a couple of moments that he said he remembers very vividly studying Theory of Statistics 1 in 1956 with Belz, not Statistics 2, but he remembers particularly Statistics 1 and Sampling Theory in 1958. So he remembers that time very vividly himself. So I studied second and third year maths, stats and inference with Professor Ewens at Monash. And he was an influential figure for me because he really introduced me to mathematical statistics. He had an enthusiasm in his teaching for things that could otherwise be thought of as dry, like distributional theory, estimation and inference, that was infectious, at least to me. And he encouraged me to consider doing a PhD at a time I didn't even know what a PhD was. So I feel very fortunate to have had the opportunity to study under Warren Ewens, who himself studied under Belz. So at the end of this talk tonight, I'll be a Belz lecturer who was a student of a Belz lecturer who was a student of Belz. So does that make a sort of Belz grand student? And I'm sure there are other past Belz lecturers too who would fall into that category. So a brief outline, what I'll talk about, and I'll come back to this in a bit. I'll talk about randomized trials, what they are and why, and then I'll give 3 examples that I've worked on over the period of time that I hope you'll find interesting, and then come to some closing, just very general comments about trials in the future. So for randomized trials, here I've got it's a relatively cheesy graphic that I've got courtesy of a clinical trials ethicist, Charles Wire, who I've worked with a bit in Canada. And it's been wonderful discussing ethical issues in trials with him. So going well outside the statistical viewpoint and talking ethical issues. So in randomized trials, you have what's called a trial population. They're the patients for the particular trial. They're randomized individually to either receive an intervention or a control, and then they're followed up over time, and an outcome event may have occurred or not occurred. That's for a binary outcome. And here we've got green is an event occurred and black is not occurred, but that's not particularly relevant here. It's just so there's the randomization and then there's the follow-up of patients. So pretty straightforward there. So a bit of background, and I hope you don't mind if it's a little bit self-indulgent, but I hope you don't mind too much. So at one stage I thought randomized trials were pretty routine or vanilla, and actually that might have been my first idea for the title of the talk, but I changed my mind on that. So I came from a math stats background. In stats classes, we learnt about 3 core randomization virtues. Firstly, unbiased allocation, so people can't choose, or clinicians can't choose which treatment patients get, so it's unbiased. The second one is that randomized groups are balanced with respect to distributions of both measured and unmeasured variables. So in statistical terminology, the treated and untreated groups are exchangeable. And it's more sort of causal inference type language. The control group estimates the average outcome the treatment group would have experienced had they not been treated. So it's like counterfactual there. And the third virtue of randomization that forms a basis of statistical tests and confidence intervals. So there are various ways you can look at this. Could be from pure randomization perspective with randomization tests and inverting them to get confidence intervals, but there's a whole literature on model-based methods, or parametric model-based methods being actually very close approximations to randomization-based methods. So is everything really simple and the methods really not of great interest because it's all covered here? So as Emmy said, I did my PhD in statistics at Cornell University in the USA, and I entered the program not being particularly interested in applied statistics at all. So I only got my first taste of applied work in my second year of my PhD when I started working with a stats professor who was doing some consulting with a New York hospital with observational data on artificial knee joints. This is way back before these joint replacement surgeries were really popular. And that got me interested in working with real data. Then later in my PhD, I decided to sit on a class called Statistics in Clinical Trials. I was really expecting to be bored in that subject, but it was eye-opening and fascinating. And it was fascinating because of the other students that were in the class. So there were students from multiple application disciplines, some in sort of clinical medical areas. I remember there was a student in optometry, a veterinary science student, psychology students, and they were all doing randomized trials as part of their doctoral work. And their questions regarding their own studies were just way outside the box of the standard methods that I had naively thought that randomized trials were all about. So it was from exposure to real-world data and trial applications that I became interested in applied statistics and then moved into clinical trials methods applied to practical problems rather than just clinical trials theory as theory's sake. So in this talk, I'll discuss a series of examples where interesting, in quotes, methods or unexpected results emerged from some randomized trials that I've been involved with over time. Of course, interesting is in the eye of the beholder, but I'm hoping that will be the case. So a bit more detail of the outline then. I'm going to be covering 3 randomized trials. And I've given them all little catchphrase names. The first one's called Please Don't Wake Up. This is not for the audience, that's the title of the segment. The second one is When More Can Be Less, and the third one is By the People, For the People, Gaining Trust. These will be 3 different sorts of randomized trials and different issues that arose. And then I'll close with some general comments. So this first segment is Please Don't Wake Up. This is about a trial to try and prevent awareness during general anesthesia. And I got some rather silly graphics here about, down the bottom here, about people waking up during surgery, but it's actually very serious business. And here's a photo of an open heart surgery here. And this is not a procedure you want to have someone awareness of if you're undergoing it. Now, this chap in this photo here, that's Professor Paul Miles, an anaesthetist that I've worked with closely over a number of trials over a period of years, and I've been very fortunate to have had the opportunity to work with him. And he's the lead, he was the lead of this trial I'm going to talk about. Then this photo below, that's me, and that's our wonderful SSA National President, Jess Kaiser. So both working in trials in anesthesiology, and we thought it would be a good idea to go and view an open heart surgery ourselves and see what's involved in that. So this was taken just before we went to witness a procedure like this particular graph. So awareness in surgery is very bad, and there was an article in the Herald Sun, this is 20 years ago now, called The Silent Agony. So a surgeon's scalpel slices through your skin and a major operation begins. You hear and feel everything but remain paralysed. And then a patient's report. I tried to scream. In my mind I was screaming, but no sound came out. So it's very important not to have any awareness during anaesthesia, and patients, it's a major traumatic event, and there can be long-term sort of traumatic consequences for patients. So courtesy of Paul Miles, I'll just give a 15-second description of the different aspects of anaesthesia. So it's called the triad of anaesthesia. So you don't want patients to move around while they're being operated on, so they have muscle relaxants. You don't want patients to feel any pain or any sensation, so they have analgesics. And you don't want patients to be aware, so they take what's called hypnotic agents. And anaesthetists spend years and years training in order to judge how much of these things to give to patients, so the patients have a good experience during their operation, so they don't have any awareness, any pain, etc. So that led to the idea of people do have awareness. It's quite rare, but there is awareness during trials. And there was a monitor that was developed by a company called a bispectral index monitor, which was developed to try and guide the anaesthetist into maintaining the appropriate level of anaesthesia. So that led to a trial led by Paul Miles about bispectral index monitoring to prevent awareness in anaesthesia. It's called the Be Aware randomized control, the BMS randomized trial. So in short, here's this monitor. Remember, this is 20 years old, so I'm sure it looks a bit better now. But this monitor is supposed to track the depth of sedation. So the patient has a series of electrodes placed on their skin, and that monitors the electrical activity of the brain and creates what's called an electroencephalogram. So what this monitor does, it uses Fourier transforms of various sorts and comes up with a single number to represent the depth of anaesthesia. And the target range for that number is between 40 and 60. So when anaesthetists use this monitor, they're told to keep it within 40 and 60 plus do all their regular monitoring. So there was lots of, and a score of 0 on this monitor means that there's no brain activity at all, which is extremely bad. And a score of 100 means the patient's completely awake, which is also extremely bad. So that's just, crude calibration of it. There was lots of observational evidence with anaesthetists using this monitor in practice, and it had been approved by the FDA as being safe. But it needed a proper randomized trial to show its proper sort of proof of concept that it worked. And that's what I'll talk about today. So the randomized trial essentially was patients undergo anaesthesia, then either the monitor's turned on or off. So the anaesthetist either uses the monitor to help guide them or they don't. So the statistical issues in this trial design. So the awareness is a rare outcome, and it occurs in about 1 in 1,000 patients, 0.1% of patients. So you're going to need a massive trial to detect even a small benefit of this monitor. And just rough calculations show you need over 100,000 patients. So that's not going to be feasible. So in discussions with the clinical people, it was, oh, excuse me, something's happened to my screen here. Oh no, that's fine now. Oh, I'm sorry about that. Yeah, so in discussions with the clinical researchers, it was decided to look at high-risk patients only, for example, those undergoing cardiac surgery, in which there's about a 1 in 100 incidence of awareness. And again, that was from observational studies. Then there's a lot of discussions about what size effect would be needed for such a monitor to be taken up into clinical practice routinely. And it was decided there needed to be a massive reduction, like a 10-fold reduction. So reducing the 1% incidence to about 0.1% incidence. And there was lots of discussion with the clinical researchers about what's going to be needed for practice change, and specifically in terms of the evidence for results to have plausibility, where evidence is really the number of events, the number of awareness events that you need to see for results to have plausibility. So continuing on the statistical issues, for rare events here, the power of a test with rare events typically depends on the total number of events. And here, because there's rare events and a binary, just awareness or not outcome, the analysis would proceed by Fisher's exact test, and the power with rare events here is closely approximated by a one sample distribution. So once this approximation was made, that made what may have seemed like a difficult sample size, or determining the size of a study problem, into something that was quite feasible. And then after a series of calculations and seeing the sawtooth power function of the exact binomial distribution, it was found that 12 events were needed for 80% power to detect this large 10-fold reduction from 1% to 0.01%. So 12 events were going to be needed, so they anticipated that 2,500 patients would give 12 events, but if we didn't have 12 events after 2,500 patients, the trial would actually continue on until there were 12 events. And then it was also important that if the event rates were as anticipated, around the 1% versus 0.1%, that your confidence interval is going to be narrow enough to give you a reasonably useful range for what the true risk reduction might be. And I'm using the word risk reduction and odds ratio here. There, with the risk ratio is a very good approximation. Is a very good approximation to the odds ratio when events are rare, so we can use them interchangeably without any issues. So the confidence interval here would show about a 37% risk reduction here, and that was thought feasible if the trial continued on to execution as planned. Then there are a whole lot of issues about how do you know when a patient says, oh, I was aware about something or other, I heard this, that, I felt pain, how do you know that it really happened? So there was a whole adjudication procedure that was developed, and this took months of to and fro with the investigators to work this out. So the results of the trial at the end of the day, there were 2 events with the bispectral index monitor and 11 events with standard care. So a little bit similar to what was anticipated, but not quite the 0.1% versus 1%. It was a little bit attenuated to what was anticipated. The odds ratio was 0.18, and then the upper end of the confidence interval indicated that it's plausible that there's at least a 16% reduction in the risk of awareness. So this trial gained immediate attention worldwide, and it's now been adopted into Australian USA guidelines for patients at high risk of awareness. And there have been further trials in more general sorts of patients with more mixed results, but that's not really of issue here for this talk. So all the lessons learned here from this. So this was my first trial in anaesthesia. This was a high risk trial. You didn't want to be harming patients, that's for sure. And it was quite nail biting. I was aware as the events were accumulating blindedly to which group they were in. And then at the end of the trial, we knew we had 13 events, but it was quite tense when there's only 13, n equals 13 data points, and you're making big trial decisions based on that small number of data points. It turned out to be a reasonably clear-cut result here, but that's certainly not necessarily going to be the case. And the most rewarding aspect for me was really getting embedded very closely in the trial, even while it was ongoing. So I don't want to spend too long. These were some of the reported occurrences of awareness. I'll just pick a couple here. There's a patient undergoing coronary artery surgery. That could be like a bypass. I heard noises and voices during surgery and the pain of people trying to tear my chest apart. So that's pretty horrendous. And here's an awful one. This is a heart-lung transplant operation, possibly the most complex operation you can have. Heard the surgeon saying, "This is more difficult than inspected, and please call for the chief surgeon." So it's staggering. You can't even imagine being in that position where you've got the awareness, you know, your life's literally on the table there, and then you hear these things going on. Okay, so that's my first tale there. That was my first trial in anaesthesia, and I found it a great experience. The next two are both cluster randomized trials, so I'll give another little cheesy schematic here. This is for cluster randomized trials now. Now there's the population that's grouped into clusters. So they could be households, hospitals, villages, etc. Then it's the clusters themselves that are randomized to the experiment or the intervention or the control, and the outcomes measured on individuals. So the intervention is delivered to the cluster, but the outcomes on individuals. So I'll give a very brief description of the impacts of clustering and why that's important. The main issue that the observations of the outcomes of individuals within a cluster are going to be more similar than the outcomes of individuals in different clusters. So this leads to a within cluster correlation, often called an intra-cluster correlation. And it leads to a loss of information relative to independent observations. And the greater the correlation between the observations, the less sort of independent information you have in a cluster. And for a given amount of correlation, the larger the cluster size, the greater the amount of information loss. So this information loss is typically referred to as a design effect. And for those of you who've got a background in survey sampling, particularly cluster sampling, this is exactly the same design effect that occurs there. So I'll move on now to the second trial, and this is called When More is Less. This is the Melbourne Water Quality Study. So I'll give it a little background for that. This was thought of in 1995 and finished in 2000. So the main premise of this was whether gastroenteritis in the community, or the gastro bug, is caused by poor water quality. So this stemmed from a couple of trials in the early 90s in Canada, a couple of randomized trials where they concluded that about 35% of gastroenteritis was due to water. But is that going to be the case in Melbourne, where Melbourne's water is pretty pristine? It's got protected catchments, a closed distribution system, the water's chlorinated but unfiltered, and so the question in the Melbourne Water Quality Study was, does Melbourne's water need filtering? So very briefly, here's a map of Melbourne's water supply. The little blobs in black are the various dams or reservoirs, and the red and green lines are the distribution systems. So 90% of Melbourne's water is from protected catchments with no farming, no human habitation, and no recreational activity. So pretty pristine water supplies. So in terms of the study design for this trial, it was a cluster randomized double-blind trial in households where the intervention is a water filter unit fit under the sink to remove the microorganisms or the bugs from the water. An identical looking sham filter, so it looks the same, it just doesn't actually have the filter operated. And the households were randomized to filter or sham, so not the individuals, the households as a group. So the design aspects were that households were instructed to drink all water from the filter tap. We're going to monitor people over a 15-month period. They're going to fill in a health diary with their gastro symptoms, and you can read these nasty gastro event definition for yourself there. So with the further design aspects, the expected gastroenteritis rates were 1.6 per year in children, so 1.6 gastro events per year in children under 10 years of age. And then to keep things simple, and from the observational data we just classified anyone over 10 years and called them adults. And the gastro event rate was about 0.65 per year. So in children, it's about 2.5 times that of adults. So children are going to be contributing more information in this trial than adults. So we want to choose an area to study that had lots of young families. So the idea would be to choose newer housing areas, also because they've got young families, and also because the modern kitchens have got room to install the filter underneath the kitchen sink. So briefly, the locations were, just remember this is going back 20 plus years, to areas fed by the Cardinia and the Sylvan reservoirs. You can see from these list of suburbs, if you think back 20 years, these were pretty newly established suburbs. So the sample size components here. So we wanted to, the target was to estimate the rate ratio comparing the filter to sham adjusted for age. So we assumed that the rate ratio would be the same, comparing filter to sham would be the same for children as the same for adults, the over 10s, and we want to estimate this common rate ratio. Because the number of gastro episodes is a count, we assumed a Poisson distribution, we allowed for this intra-family correlation in the form of cross-infection, because gastro will can spread across families, so we allowed an intra-family cross-infectional correlation of up to 0.4, and we wanted to detect a 15% reduction in the gastro rates when using the filter compared to the sham. So with the sample size formula, we used just standard Poisson regression and then derived a variance expression to account for the intra-family correlation. So then there are issues of how many children do we want to study per family. So here's the first of a series of graphs that I'll show. So this graph on the vertical scale here is the power for this Poisson regression analysis, and on the horizontal scale is the within family correlation. And these three lines represent 2 adults, 1 child, 2 adults, 2 children, 2 adults, 4 children. So clearly 4 children has uniformly greater power than 2 children, but the power drops off with the size of the correlation. That's because we get less information as the size of the within family correlation increases. So expect the power curves to drop off. So the sample size, I haven't come to the nub of it yet, so this is all just the background. The sample size was 600 families where we're aiming to recruit 2 adults and at least 2 children on average. Allowed for an intra-family correlation up to 0.4 and 80% power to detect a 15% reduction. And the trial was conducted in late 97 to early 99. I'll talk about that later. But towards the, at the end of the trial, before it actually was published, I decided to give a short talk about the trial at a biostats conference. So I did some new graphs. So here is the power curve with 600 families. This is for Poisson regression power with 2 adults and 2 children. And this is just taken from the previous graph. So the power decreases. Then the question was, what happens if you have 4 adults rather than 2 adults? So this green line now is the power curve with 4 adults and 2 children. This crosses over. What on earth is happening here? Power can be lower. So once you reach a certain cutoff correlation point, the power with 4 adults can be lower than that with 2 adults. So you've got more people in your trial, but you've got less power, you've got less precision, you've got higher variance. How could that possibly be so? I was convinced I made a mistake, and so I checked it and then checked it again. But then I had to sort of step back and think about a little bit more. And this is where when more can be less comes in, and I'll just spend a moment to explain it. This has got a bit of first year stats in here, so if there are any children in the room, maybe you want to cover their eyes not to frighten them. So let's take just a simple first year stats type example. We've got a normally population, a normally distributed measurement, normal mu sigma squared, and we consider two independent random samples from this population. Our goal is to estimate the population mean mu. The samples of different sizes. We've got sample sizes of N1, first one, and N2 is the second one, and the second sample is smaller than the first sample. We have sample means y bar 1 and y bar 2, and because the second sample is smaller than the first, the variance of the second sample mean is going to be greater than the variance of the first sample mean. So the question is, will combining the two sample means into a pooled or combined estimate always lead to more precision than just using the first sample alone? Some of you will know what the answer is going to be to this, but I will go through it. For example, let's take our pooled estimate as the unweighted average of the two samples. So despite them being of different sample sizes, we'll take the unweighted average of the two. So we're assigning equal weight to the first and the second sample mean. It's easy to show that the variance of the pooled sample mean is going to be greater than the variance of the first sample mean if the second sample is sufficiently small relative to the first sample, and it's less than 1/3 the size of the first sample. So including the second sample in our estimate actually makes us worse in terms of precision if our combined estimator is not weighted in a proper way. Of course, the better way to do weighting is by inverse variance weights, and doing that here, it always gives a weight greater than half to the first sample because it's larger, and the optimal weighted combination is just the pooled sample mean, combining both together. So the little moral of this story, which I expect many of you would know already, is that very suboptimal weights can reduce precision even when including more data. Could this also have been the case for the water filter trial? So a little bit of terminology, just a tiny little bit here. We're going to be estimating the filter effect in adults and children. We're assuming it's a common filter effect, common rate ratio, but with Poisson distribution and Poisson regression, the natural link function is the log link. So we're going to be looking at the log rate ratio, which I'll call beta. And we've got estimates of beta in adults, beta hat A, and children, beta hat C. So we've got two different estimates. So we estimate this common beta by beta hat. This is our sort of combined estimate using model terms for filter sham and a binary covariate for adults and children. So the effective filter status adjusted for age, you could call it. And now Poisson regression, being a maximum likelihood procedure, it's very closely approximated by inverse variance weighted average of the estimates in adults and children, with the weights calculated under the assumption of independence between individuals in the family. And these, the weights given to the adults and children depend on the event rates, the number of adults and the number of children. They don't depend on the within family correlation because we're using standard Poisson regression for our estimation. So the question is, how far are these Poisson regression weights from the optimal weights which do take into account intra-family correlation? Could we actually be in a situation like the two sample means example where we're adding in extra information and we're doing worse because of suboptimal weighting? So here is a graph now. On the vertical scale is the weight given to adults in Poisson regression, and the horizontal scale is now the number of adults. So I'm fixing the case where we've got 2 children per family, and this within family correlation is 0.4. So the Poisson regression weights increase with the number of adults. So this is saying the greater the number of adults, the greater Poisson regression is giving priority to adults over children. And the optimal weights, which do take into account correlation, increase very, very gradually. and almost asymptote there. So the Poisson regression weights are giving way too much weight to adults than what the optimal weights are. And this gets worse with the increasing number of adults. So the question is, how does this affect the variance of our Poisson regression estimator? And we see, in fact, that the Poisson regression variance, so this is an analytical variance, not too difficult to write down, for Poisson regression increases with the number of adults. So this is saying that we've got more adults. We're going from 1 to 2 to 4 to 6 to 8 to 10 adults. With each increase in number of adults, we're losing precision. So with more adults, we're losing precision. So more is less here. This doesn't occur with the optimal weighting. There is, though, the variance decreases. It's ever a slight decrease, but it decreases nonetheless. So let's now go back to our initial power crossing graph, which is what got me scratching my head in the first place. And this is where the lines crossed at some correlation value, and beyond that, and the correlation of 0.4, the values we looked at, the power with 4 adults is smaller than the power with 2 adults, so more is less. Let's now look at the optimal weighting, and this paradox is completely resolved. At the point of 0.4, we've got barely any difference between 4 adults and 2 adults. And what we see is there's always some benefit of 4 adults over 2 adults, but that benefit diminishes very quickly, really. And by the time you've got a correlation of 0.4, there's almost no value of 4 adults, but you never reduce precision. So the moral of this whole exercise, and so this was the unexpected twist and turn that I discovered, is more data does not necessarily lead to more precision or power unless your data is combined sensibly. And even with a standard method like Poisson regression, you really need to know how the pieces are being put together in the regression, because you can get some very strange results and some very undesirable results. So let me just quickly go to the results of the water filter trial. There are on average 1.9 children per family and 2.8 adults. So we had more adults and slightly less children than were anticipated. And the event rates with the real filter were 0.79. This is pulled over everyone. 0.79 per year with the real filter and 0.82 with the sham. So very little difference there. The analysis was done with called a marginal generalized estimating equation model with sort of a Poisson distribution. The offset was the amount of observation time per individual. We used exchangeable correlation and a robust standard error in case the exchangeable correlation was misspecified. We adjusted for age, sex, and region, and this was all pre-specified, and we got a rate ratio at the end of the day of 0.99, and the confidence interval could indicate possibly up to a 15% increased rate of gastro with the filter, or 15% reduction. So this was as close to a nil point estimate as you're going to get. I mean, a rate ratio of 1 would actually be a nil effect, but there was some uncertainty, and the event rates were slightly lower than what we'd anticipated. So we got a little less precision so that we thought. But anyway, there was certainly no conclusive evidence that filtering the water would definitively benefit Melbourne, and so filtering the water hasn't happened. Personally, I would have preferred a slightly larger trial with less uncertainty, and it was a little unfortunate that we had a greater amount of uncertainty than what was planned initially. Okay, for my last example, it's changing tack changing tack greatly, and this is again a cluster randomized trial, but a completely different sort, calling it by the people, for the people, gaining trust. And this trial is the RISE trial, Revitalising Informal Settlements and Their Environments. taking place in Indonesia and Fiji. So this is a cluster randomized trial and informal settlements, and this is a typical informal settlement. You can see it's not in great shape. This is the largest trial I've ever been involved with in terms of the collaborators. There are 25 industry, academia, etc. collaborators and over 150 research staff. And here's a snippet of just some of the people involved. And I do want to pay particular attention to Professor Julie Simpson from University of Melbourne, who's Professor of Biostatistics there. And it's been an absolute pleasure to be working with my good friend on this trial. We've had lots of tricky issues to talk about and work about together, but we're getting there. So a bit of background here. 1 billion people live in urban informal settlements globally. It's a massive problem. 2.3 billion people worldwide lack adequate sanitation, and over 500,000 children under 5 die of diarrhea each year. So the vision of this RISE trial is to have a novel approach to water management in these informal settlements to improve the human, environmental and ecological health. So here's a before and after picture. This is actually the same settlement just before and just after a huge flooding rain. And you can see like the clothes, it's actually the almost the same clothes on the line there in the two. So this is, you know, very close in time between these two before and after the events. So you can see a massive flooding event, and the environment is not very clean. Even when there's no flooding event, there's animals, you know, roaming around and droppings everywhere. There's young kids and, you know, leaving things, droppings all over the place as well. And then the rains come, the floods come, and this just gets dispersed everywhere. So the idea of the RISE intervention is to reduce vulnerability to flooding such like this, you know, largely due to climate change, recycle wastewater, harvest the rainwater for drinking, create green space for water cleansing and food cultivation, and to restore the natural waterways to encourage sort of diversity of species. So the research aim is that, so this is it's a sort of a pathway type intervention. So the water sensitive revitalisation will change the physical environment. That could either change human health directly, or it can change the ecological environment. And the sorts of human health outcomes we're interested in are basically the gut health, particularly in children, and the psychosocial well-being of all inhabitants in these informal settlements. So the study design challenges in there. The first one was, could randomisation even be used? You have to get consent from settlements to participate in trials, no different to anywhere else. You can't just tell them that we're going to be doing intervention, you know, in your area. But after lots of discussion with the local researchers and liaison with the community leaders, it was realised there could be what's called a wait list control design. So the intervention could be implemented early in half the settlements and then late in the other half of the settlements. So the communities had familiarity with lotteries, but not with randomised trials. And so it was the local researchers worked with them in the language of lotteries to then explain a randomised trial. So the design of the trial is a longitudinal parallel arm cluster randomised trial of early versus late settlement revitalisation. And there are multiple layers of clustering to consider. The sample size was terribly difficult. Had to derive new formulae and lots of simulations, and it ended up with 12 settlements per country being the required sample size. So now for the randomisation, there's 12 settlements per country, so there's Indonesia and there's Fiji. So in each country we randomly allocate 6 settlements to early and 6 to late revitalisation. So there are 853,000 possible allocations. But some of these allocations, with only a small number allocated in this trial, with only 24 settlements in total or 2 countries with 12 each, there's the potential for huge imbalances in absolutely critical variables like density infection risk, which is measured sort of proxy by the number of children per settlement, vary quite a lot across settlements. The flood risk varies greatly depending on the geographical location of the settlements. and the assets, the actual possessions of the households in the settlements also vary quite a lot across the settlements. So we constrained the allocations to be the best balanced 60 allocations per country on these three critical factors. And that led to a possible 3,600 allocations possible, but with doing the randomisation separately within each country had only 60 allocations per country, and I'll see in a moment why we restricted it to a number like 60 and not say 1,000. So the implementation challenges are what I want to talk about from here. The randomisation has to be culturally sensitive to communities and it has to gain their trust. It is completely unacceptable for, say, me or for Julie to go and write some little code and say, oh, these particular settlements are going to be allocated to the early intervention and these particular ones to the late in ones. That is completely unacceptable in this setting. So communities need to see themselves a transparent and clearly unbiased randomisation process. So this required a public randomisation ceremony, and that the randomisation is going to be for the people, by the people. So Julie and I spent a long time working out a process for doing this, lots of visual aids, lots of outputting files to Excel sheets, as you'll see in a moment, and it's very far from any randomisation I'd ever prepared previously. So the randomisation was held in Makassar, that's the city where, the Indonesian city where the trial's being held. This was in March 2019. So 180 people attended here. There were heads of government departments, heads of city districts, heads of each of the settlements, and so they were all there to witness this randomisation ceremony. So the 60 randomisation allocations was partly chosen because we could put them up on a wall in a room, and so everybody could see every possible allocation. Like, for example, allocation number 21 out of 60 shows the first 6 are the names of the settlements getting the early intervention, and the last 6 are the names of the settlements getting the late intervention. And so it's clearly here what each number represents. And here is the randomisation toolkit. It's not a piece of our code. It's a set of ping pong balls, handwritten with numbers 1 through 60 on there. There are actually 2 trays. There's one underneath there. There's this bowl, which we're going to put all the balls in, a couple of bags of rice, so you see the balls less, and then some gifts, as we'll see afterwards. So each settlement sat at a separate table in there, and each settlement got a lottery card with almost the 30 winning numbers to be the early intervention and the 30 late numbers. So you can see here there's 2 columns on there. So each settlement knew, so there's 30 numbers there from 1 through 60 and the other 30 numbers from 1 through 60 there. So now I've got a short video of a snippet of the randomisation ceremony. So the reactions and conclusions are reactions that we got from the people who were at the ceremony, that having the children created a sense of fun, as well as reinforcing to everyone that the selection of the number was in fact down to chance. And with a bit of chaos, the communities actually now understood that they'd been allocated to early or late intervention. So this randomisation was a great success. So this was completely unexpected at the start of the trial that we'd have to be doing this, but it was another richly rewarding randomisation experience. It needed lots of detailed planning and transparency of every step, but no statistical coding there. And a very far cry from the usual code-based randomisation that it was involved in. So current status of the trial, the randomisation is complete in both countries, and the construction's about to commence, and it'll take about 12 months to do, and then we've got a 2-year follow-up to see how well this intervention works. And there are going to be some great opportunities for some fairly complex analyses across pathways from intervention to environment and ecology to human health and well-being. So that's for the randomisation component. Now for the last couple of minutes, I want to make some brief and probably way too sweeping statements and thoughts about recent advances in clinical trials and the future. So there's a big topic now about big data, as you know, big data, and the idea of a concept called real world evidence. And specifically in the health area, there's so much health data around, real world health data, not artificial data from trials, but real world health data from out in healthcare. Because we've got big data, do we need trials at all now? So the big data comes from hospital and medical records and clinical notes. So there's lots of observational data. So can we do observational data analyses and we don't need trials anymore? The big sticking point, there are a number of sticking points, but the big one is we can't ever ensure we've got the absence of what's called unmeasured confounding, which is really, what are the reasons why someone's treated with drug A compared with drug B, or method A compared to method B? In randomized trials, it's by chance. So we understand that, but we can never be sure that we've captured all possible reasons why people are treated with one versus the other. So there have been proposals for automated high-dimensional machine learning propensity score calculations or estimation of treatment effects. That would be fine if you've captured all the variables. You can then use fancy machine learning techniques, or similarly high-dimensional modelling of outcomes. The key part is you've got to have the right source data. And is that there? Have you captured all the factors that affect why some people are treated with one rather than the other? It's highly unlikely. So what can all this real-world data, real-world evidence provide? I'm going to sort of claim that it can be used to suggest treatments for randomized trials. But to be even to suggest treatments, you need to use really, really careful causal inference methods using a technique called the target trial or the hypothetical trial, the concept of analysing observational data like a randomized trial. But well-conducted randomized trials are still the gold standard. The second very broad area is about novel trial designs, which are adaptive trial designs. So there are many. I've only talked about simple parallel trial designs where you randomize to A or B. There are many variants of designs for faster, more efficient trials. And adaptive trial designs alter the design of the trial mid-course. You could drop treatment arms, you can add in new treatment arms, you can change the randomization allocation ratio. Instead of 50-50, it can be based on how well different treatments are performing. You can update the sample size whether you've looked at the data or not. There's all statistical formulations done to be able to ensure the validity of all of these. And perhaps the most complex form of trial are called platform trials, which are perpetual trials. There's no end date to these trials. They continue on perpetually. There's multiple domains or classes of treatments, multiple different types of patient groups, all studied within the large platform. And some of the major COVID-19 treatment advances or ruling out treatments that didn't work have come from platform trials. One here in led here in Australia, another one, a big recovery trial from over in the UK. And an example is the REMAP CAP trial, which essentially has multiple mini trials, 14 domains of treatment, studying 50 treatments simultaneously. And that's using a Bayesian framework because that's by far the most flexible framework where you're calculating either posterior probabilities of a treatment being best or posterior predictive probabilities projecting out to the future to see what would happen, to see if drugs are not worth persisting with in the future. And the final comments are just some comments about so-called personalised medicine, which is really treatment effect heterogeneity. So the argument is that randomised trials estimate the average treatment effect in the group that were in the trial, and then you generalise to a group that's similar to those patients in the trial, and then the randomised trial gives you the average effect, not the effect for an individual. Typically in clinical trial papers, there's some, they call it subgroup analysis, which are really interaction analyses, where factors are sort of included in an interaction term one at a time, and these could be sex, whether the treatment effect for males compared to treatment effect for females, or older people versus younger people. So they're pretty coarse subgroups. What about for fine subgroups? Once you go looking at fine subgroups, you're going to be leading to small sample sizes. You've got multiplicity issues and potentially leading to spurious results. But fundamentally, the treatment effect for individual patients is not identifiable because patients only receive one of two treatments. The exception is in N of 1 trials or multiple crossover trials, but these are not trial designs that can be used for every condition or every type of treatment. And moreover, there's a general question of, does heterogeneity actually exist between patients in the treatment effects? So there's been a lot of hype about this, people saying, yes, it's good, not good. But there hasn't been, until last year, there hasn't been a systematic approach to how this can be developed. And there was a guidance document called the Path Statement, Predictive Approaches to Treatment Effect Heterogeneity, put out last year. And its goal is about sensible procedure, sensible, rigorous and reproducible procedures for individualized prediction of treatment effects. It's got two main types called risk modeling or effect modeling. Basically, risk modeling is you stratify on risk, so your effect modification is according to risk, or effect modeling is where essentially you do use machine learning, data-driven subgroup identification, and then separate validation exercise in another data set. So these are promising approaches, but more data is needed. So the promise of personalised medicine hasn't really appeared yet. So final conclusions here. The field of randomised clinical trials is rich and diverse, lots of applications. It's very far from routine vanilla. Rather than a statistician, you might think of a statistician being involved in the design and analysis. There are lots of different aspects. You'd be involved in the randomisation, the conduct, the reporting, the interpretation, and the communication. So far more than being a mechanical number cruncher, you really get involved as a key member in the study team. You often see the impact of your work almost immediately, and there's a real feeling of making a difference to society. And from the methodological standpoint, it's a great area because methods are constantly enhancing, new designs being come up worldwide. So I'll close with saying that I certainly do not think it's routine, and I'm very pleased in my doctoral studies that I saw the light and moved towards applied statistics. Here are some references from the various trials. So thank you all very much for your attention.
Thank you very much, Andrew. If you would like to use your emoticon to give a reaction of a clap, please. And also, there are questions. Maybe what I can do is, if you have a question, if you could raise your hand, and then you can also speak it out. If you can also write it in the chat. What I might do, because Ian has written a question, I like to, if Ian, you like to, I like it, if you want to unmute yourself and you can ask, otherwise I can read out your question.
Thanks, Emmy. Yeah, thanks very much for the talk, Andrew. It was really great. I was just wondering, in the water filter randomised controlled trial, you had a plot where the variance decreased very slowly with increasing numbers of adults. And I was wondering if you'd comment why it decreased so slowly with the optimal weighting. Is it because of the within-family correlation or for some other reason?
No, it's exactly because of the within-family correlation there, that the adults contribute less than children because their events rate's lower. And then with a within-family correlation of around 0.4, they're really providing very, very little new independent information. Yep. Yes, you're exactly right there. There's a little backstory. I don't know if you remember, Ian, that I came to see with the results of this trial. We needed independent verification of the results of this trial, if I remember right.
Yes, I do remember that.
That goes back a long way. But I hadn't seen this crossing power curves issue at that time, because I certainly would have discussed it then.
Yeah.
Yeah.
Sure.
I can see some other messages here in chat, Emmy.
That's why there's a lot of thank you messages, and just scrolling back. So Khalib has a general question. With real-world trials, what do you think of the FDA accepting them now under the 21st Century Cures Act? And how good is EMR data? And how can it improve in terms of immortal time and causality for observation trials?
Okay, yeah, yes, I found the question. With real-world trials, I think do you mean real-world evidence from observational data rather than real-world trials? So that these are not trials, these are observational studies. I think, yeah. So real-world trial, there's a whole area called pragmatic trials where you basically take all patients that come along very generally, generally inclusive patient group to be studied in a randomized trial, so the results are more generalizable. But I think the real world evidence, the question might be, the FDA accepted. Look, I've got cautions about that, and it's related to the second question: how good is EMR data? I can't answer how good EMR data is. It covers things and it doesn't cover things, and it's going to be different hospitals, collect different amounts. But I'm sure it doesn't collect everything that you need to be able to differentiate why patients get one treatment over the other. And how can it improve in terms of mortal time and causality for observational trials? Again, as I mentioned, there are biases, but in terms of immortal time, you've mentioned immortal time there, that's when if you're looking at one patient's taking a drug at one time, one patient's taking a drug at a later time, the second patient has to live long enough to take that drug at that time. So there can be that patient's had to live longer in order to get into the study. So that's a very crude explanation of immortal time. But by using this target trial approach, there's publications in the epidemiological journals about that. One can generally get rid of immortal time bias, but generally one needs to use very careful methods from the causal inference literature for making any sorts of causal claims about treatments from observational data.
Thank you. We also have a question from Alan Cheng. So how do you go explaining complex statistical issues to clinicians?
Oh, I asked Alan Cheng to do it for me. Alan Cheng is our
Can we do that as well?
Diagrams. Let me just see. So I haven't seen. Just complex statistical issues, just in general. I try and break them down into simple components and then build them up. As you know, Alan, we had a non-inferiority trial where we wanted to show the particular drug wasn't that much worse than another drug. And then so we had technical issues of non-inferiority margins and things, and there was lots of difficulty with getting the concept across to investigators. But in the end, it was breaking it down into simple pieces and with as many diagrams as possible. And so that's my general that's my general recommendation. In terms of observational studies, I just want to give a plug to causal diagrams or directed acyclic graphs, which are the most intuitive mechanism I've come across to be trying to understand the nature of a problem, where the researcher, the health researcher of whatever form, or social science researcher, whatever field it might be, needs to write out how the different variables, the different quantities link in together. Really helps with refining of research questions, refining of data analysis, and also refining of data that needs to be collected as well.
I think your slides also speak what you say, because you had this animation of how the randomization was occurring or was measuring. And I thought that was actually quite a nice diagram.
Oh, I swiped that, so I can't claim. Can't claim that for mine.
So we have also another question from Jason Jin. So hi, Andrew, what's your thought on dynamic borrowing from observational studies to control arm in clinical trials?
That's a critical technical question. I've had no personal experience with that. So you're taking data from observational studies and using them as part of the control arm in there. So in the control arm, to boost up the control arm, there's always concerns. So the key, again, thinking back to the causal nature, you've got to think about exchangeability between the control arm in your trial and the data that you're borrowing from the observational study. How and in what ways are they different, and how can things go awry? So that's my simplistic answer there. I haven't got personal experience having done it, but always cautious when there's any incorporation of external evidence, specifically from observational studies, because the data that you're borrowing from this observational study, these are not people who've been randomized into the study, so these people are not exchangeable with the treatment group either, and they're not necessarily exchangeable with the control arm either, so need to be cautious.
So we have a bit of a long question from Margarita. Andrew, thanks for a great talk. May I say that RCTs are, of course, the gold standard, but perhaps not because of a lack of unmeasured confounding. Is this not only when targeting the ITT, which is increasingly recognized to not necessarily be the estimate of interest? If you change estimate, you have confounding issues too, right?
Absolutely correct. And if you can indulge me, I might try and address that with another slide that I decided to omit for the point of time. This was randomization is still the gold standard. I won't go through everything here, but as Margarita says, exactly, it depends on the question, the estimand. So randomization addresses the question, the effect of treatment as randomized. This can be thought of as a treatment policy question. It's good under full compliance, no loss to follow-up, and absence of post-randomization events like flooding events in villages, or in a surgical trial, patients undergo other surgery, things that sort of mess up your primary outcome. So when you start getting into more refined questions, randomized trials become more like observational studies, and there's actually a continuum from randomized trials to observational studies or non-randomized trials, and it really depends on your research question is as to how much of the randomization component can really be beneficial. And there's assumptions everywhere as soon as you move away from the randomization. So I hope, Margarita, I sort of addressed it. I could have anticipated that you'd ask. Yeah.
We have a question from Gordon. Would you like to unmute yourself, Gordon?
Yeah, thanks. Whoops, I've got my wrong camera on. Never mind. Thanks a lot, Andrew. I'll just continuing the conversation about observational studies and randomized trials. It's not always a randomized trial, of course. So I work at the Walter Eliza Hall Institute, and it's not randomized trials, but it's still designed experiments where you assign treatment. So it's the same dichotomy. And we get a bit frustrated by sort of the machine learning group. It's something that's not really understood in the machine learning, but something I've been struck over the years when I've taught statistics is that we actually don't teach the difference between experiments and observational studies, and the difficulty of making causal inference from an observational study, even in statistics courses for statistics majors. So I wondered if you wanted to comment on that. When I got to lecture biology students at the University of Queensland, I made sure that I did teach that distinction. But when I was an undergraduate, I had a terrific maths stats course at the University of Western Australia, and never did we touch on the issue of causality. It was, nice regressions and generalized linear models and unbiased estimators and variance, and nothing about causality.
Yes, no, I agree with you 100%. I'm a little removed from what the undergraduate statistics programs are like these days, but certainly in the Master of Biostatistics we teach in, we've got a unit on causal inference, but we're trying to bring in these causal ideas and the basic assumptions, consistency, exchangeability, and positivity, for being able to have at least some show of making any causal interpretations. We're trying to introduce that into sort of mainstream Masters of Biostatistics, and it's being introduced in more mainstream Masters of Epidemiology, some courses around, but I'm not sure whether it's in pure statistics courses, but I agree with you entirely that it should be included within there. And there are a number of workshops that we run in the summer school, and Margarita Moreno Betancourt, who's just asked the previous question, runs a wonderful 2 and 3 day sort of causal inference course for health researchers without a huge amount of quantitative background. And so these researchers are learning early on that the difficulty of making causal statements, yet in statistics where the students should really expose to it, they're not being exposed. I don't know if anyone else can comment about the current undergraduate statistics curriculum. At Monash, I'm sure that doesn't occur, and it's certainly in the undergraduate data science, it doesn't occur at Monash. Yeah.
As a more recent graduate, I can say, yeah, it's not really taught. And certainly, I think there's a lot more emphasis on the analysis rather than the actual design of experiments.
Oh, Ian said it is taught these days at undergraduate level. Okay, that's good to know.
So we've got a question from Lau. In the RISE study, the participants seemed very keen to get on the early arm of the trial and avoid the later arm of that trial. Was the issue of clinical equipoise discussed together among participants and investigators? How do you reconcile the apparent contradiction between needing to compare treatments when the target population receives one treatment to be better?
Oh yeah, well this is in any sort of public health improvement program in a developing country where there's prima facie reason to believe that one treatment will be, or one intervention will be better than the other. The key here was having the wait list control that made this possible. We'd already thought about the first study design that was contemplated was a step wedge design where the intervention would be phased in a random order across settlements, but that turned out that wasn't going to be feasible or not. Sorry, the first part of the question, they're keen to get on the early arm and avoid the later arm. Yeah, so there is more equipoise as it first looks because the early rounds of intervention construction are being done simultaneously across all the settlements. And there's going to be a lot of learning from that on how to do this. So the part of the way this was addressed, that those who get are randomised to the late intervention get the benefit of knowing of the additional knowledge on how to avoid problems with the construction of these settlements. And there's a very fine line between learning the lessons from a settlement and then changing the intervention later. Yeah.
Intervention heterogeneity, so it's varying over time. Yeah, I think you partially answered the question. You said that potential mediation analyses will be done, so it might be that would be another reason to explore an apparently beneficial treatment in an RCT. Thanks.
Yeah, that's right. Yeah, and we've got some detailed mediation analyses planned. A few more comments about University of Melbourne here.
Comments. So if there are...
right. Oh, no, someone asked, Matt Spetol said, the randomisation scheme in the last study was really innovative and clearly valuable. How do you think journal editors will react when you publish to India for some. No, I think it's the same as computer-generated random numbers using what's called a covariate constrained randomization to picking one of 60 allocations from, and we've got basically two separate lists. You pick from 1 to 60 in one list, 1 to 60 from another. So I don't think it really matters from a technical standpoint how it's done, as long as it was done properly in the field in this public ceremony where, to all intents and purposes, we understand that it was done. So I don't think there'll be an issue with journal editors, no.
I think there's no more questions. A lot of thank yous coming through. So if you have no more questions, please join me in thanking Professor Andrew Forbes for his talk. Thank you very much, Andrew, for your talk.
Oh, thank you, Anne. I was delighted to do it, and absolute pleasure to be here.